The broadcast is now starting. All attendees are in listen-only mode.
Well, hello everyone and welcome to Mallet Technologies webinar series. Thanks for taking the time to join us today. My name is Boz Marshy. I'm the account manager here at Mallet Technology. Today's presenter is Mete Oscar. He's our HFSS expert. Just a quick overview of today's agenda. I'll give you a quick overview of Mallet Technology. Then Mete will give us the HFSS antenna design webinar. And then at the end, we'll have time for discussions and questions. At the end, I'll open it up for verbal questions. But during the presentation, if anyone has questions, feel free to type them in at the questions section of the GoToWebinar control panel. Mete will answer the questions at the end of the session, but you can type them in, as they come to you, because I understand sometimes it's easier that way. This webinar is being recorded. It will be available on our website. So if you enjoyed today's webinar and want to watch it again or pass it on to a colleague, it will be on our website. Mallet Technology is a world-class engineering software company. We combine software tools with a broad knowledge and expertise to help our clients compete in today's marketplace to produce reliable and cost-effective products. The company's been serving engineering customers for nearly 40 years. We were started as Mallet Technology started in the mid-70s as a consulting arm for Swanson's Analysis Systems by Dr. John Swanson, the founder of ANSYS. We've been an ANSYS channel partner since 1985. We were one of the first ANSYS channel partners. Our website, of course, is www.mallet.com. Our next webinar will be a webinar on ANSYS CFD on fluids. That will be 3 weeks from today, Friday, May 10th. You can register for that webinar on our website at www.mallet.com, and you can also register for that website at the ANSYS.com website under events. Mallet Technology, we also do ANSYS consulting services. We do consulting services in ANSYS structural, ANSYS CFD, and electromagnetic physics, just like we're doing today. Mallet Technology also does training for ANSYS. We'll train at one of our Mallet locations or a customer location. So if anyone's interested in training or consulting, please let us know. We also are a reseller of ANSYS software. So if there's any ANSYS software you're considering about buying, we're happy to talk to you about that. You can contact me directly at boz@mallet.com if you have any questions on any of the services we offer. So now I'll turn the meeting over to Mete, and we'll get started with our webinar portion. Give me a minute to do that. Okay, Mete, you can now take the presentation over.
Thanks, Boz. Hello, everyone. Welcome to the webinar on antenna design using ANSYS HFSS. My name is Mete Oscar. I've been using HFSS in my designs for over 20 years. HFSS has saved countless number of engineering hours and money over the years for me. HFSS has evolved over the years greatly, and it has been widely accepted in the industry and in the academic world. In the industry, HFSS is used in coming up with designs without actually having costly bills. In academia, it's used to simulate different ideas as well as a tool to verify newly developed numerical techniques. So it's a very well established tool in electromagnetics. In today's webinar, I'll be talking about several topics and illustrating details on 3 different antenna design examples using HFSS. I'll start with the drawing of the geometries. Then I will illustrate how to set up radiation boundaries and how to define ports and how to set up the actual simulation. Next, I will give examples of what kind of results can be obtained through the post-processing features in HFSS. And lastly, I will talk about some of the most common mistakes during simulation setup. So as Boz mentioned, I'll be answering any questions at the end of the presentation. So please type any questions that you might have during the presentation in the chat window. I would like to start by pointing out that we need to pay very close attention to setting up the model in simulations. This applies to all simulation tools in general, but it may sound simple, but please remember that the output of the simulation depends heavily on the input data. And wrong input data and wrong assumptions will actually result in wrong output data. In addition, all simulation tools have limits, and understanding these limits is very important in what to expect out of the simulation. For example, HFSS has multiple magnetic solvers built in, and each solver applies for different cases. And understanding the limits of each solver is key to deciding what solver to use. Today, we will be talking about the FEM solver in HFSS. It's a frequency-based solver, which is a very powerful tool in antenna design. I would like to start with the drawing of actual antenna geometries to model them in HFSS. The key to successful simulations is to have a drawing with parameters so that we can change the geometry on the fly and optimize our geometry, or the antenna in this case. Every dimension should be created as a variable if possible. Before you start the simulation, you may be thinking that you will only run it one time with one geometry, but I guarantee you that you will want to change something and rerun the simulation after the first run. And you know, why not take advantage of a model to go over what if scenarios for your design, right? So I'll be talking about 3 different geometries today. We'll talk about a coax-fed patch antenna, as you can see. We'll talk about a dipole antenna design and an edge-fed or an inside-fed patch antenna design. All of these are pretty simple antenna designs. In this edge-fed model, we have a microstrip line that's feeding a patch antenna. And if you look how I created the model, I have parameterized every dimension: the width of the patch, the length of the patch, the substrate height. You can see the substrate in red here. So if I want to change anything here, let's say I want to change the width of the patch to 9. To 9. Sorry. Or the length of the patch to 7. I can do that on the fly without any other additional editing. And these parameters can also be added to the optimizer feature of HFSS, where we can do sweeps of any parameter. So in the dipole as well, I have created a length parameter. There are 2 rectangles that I have here for the dipole. I've created a length parameter, and I can change the length on the fly, make it smaller or bigger. And finally, in the coax fed case, coax fed patch antenna case, I have parameters as well. I have a parameter for the coax size, coax length, outer radius that I can change on the fly. One thing that you see in all of these designs is this box, big box. So let's talk about this big box. So we typically would like to simulate antenna designs in free space. In order to mimic the free space in the computation domain, we will need to terminate the domain so that the outward traveling waves do not get reflected back and cause inaccuracies or change the simulation environment. For this purpose, HFSS has several different absorbing boundary options. But please remember that if you do not define a radiation boundary in HFSS, the solver will terminate the domain in PC, and this will change your results greatly if you're expecting free space results. So let's go back to this coax fed antenna, where I have defined an air box that has radiation boundaries everywhere on every surface of that box except for the bottom. The bottom surface is actually a PEC, perfectly electrically conductive surface, which represents the ground plane in this case. Let's go back. Let's go to this coax substrate, which is the substrate in between the inner and the outer conductors in this design. Notice I don't have anything defined on the outer surface for this coax. And if you remember what I said before about surfaces that are exposed to the outside domain are going to be replaced with PEC if we don't define anything. And in this case, it has been replaced with PEC. So this PEC represents the outer conductor. Some designs that are enclosed inside metal boxes may need to be terminated by absorbing boundaries. It may not need to be terminated by absorbing boundaries. So this is an example of such a case. Guided wave structures do not need to be terminated due to absorbing boundaries. If you leave them exposed like this, they will be automatically terminated with PEC. So we mentioned about the airbox. You will need to select each surface of the airbox rectangle to define the radiation boundaries. There are some general rules of thumb for selecting the airbox size. However, this really depends on your antenna geometry and the environment that the antenna is in. For example, if you are simulating a cell phone antenna and you would like to include the whole phone in your simulation model, the airbox for this structure will not be the same size as the airbox that's needed for the simulation of the antenna by itself. The structure with the whole phone will be electrically larger, so you will need a bigger airbox. Similarly, if you're interested in body effects, human body effects of a wireless device, you will need a much larger airbox. So what I would recommend doing is looking at the return loss S11 and looking at the antenna efficiency and monitor those to determine your airbox size. If the S11 is not changing as you increase your airbox size, that means your airbox size is sufficient. One thing to mention about looking at radiation efficiency, which your airbox size is, that the radiation efficiency is much more sensitive to the airbox size. And you may end up with a larger airbox size if you're interested in accurate radiation efficiency calculation. So yeah, as I mentioned, all of these have airbox and radiation boundaries defined, all of these models. The next step after drawing the geometry and assigning boundaries is to set up the excitations. HFSS offers different types of excitations depending on your simulation. For example, on this inset fed patch antenna, I've used a wave port, what's called a wave port. The wave port is simply this rectangle over here. That is touching the bottom conductor, which is the ground plane, and touching the microstrip line, which is the signal feed to the antenna, and it's extending above that microstrip feed because there are fringing fields on the microstrip line, and we want to capture those for our S11 calculations. If this was a waveguide, for example, you would not need to extend this rectangle beyond the top conductor because it would have been enclosed in a metal box, which is a waveguide. So there are no fringing fields. In the dipole case, I have used what is called a lumped port. As you can see, one thing to mention about these red arrows is in the port definitions, it's basically to indicate the direction of the integration, the line integral of the electric field. But the lumped port is again a basic rectangle that connects the two conductors, the left, in this case, the left arm and the right arm of the dipole. And in the case of the coax fed patch antenna, I have again used what's called a wave port. And the wave port, as shown here, connects the inner conductor to the outer conductor. And the red line is again the integration line that's going from the inner conductor to the outer conductor. This port is a little bit different. You can actually use the de-embedding feature of HFSS to de-embed the reference plane all the way to the coax plane, the ground plane, which will allow you to see the impedance directly at the coax feed. And the de-embedding feature is over here on the left side. The final step before running the simulation is to set up the sweep types and the convergence criteria. There are multiple sweep types. You can have discrete interpolating or fast sweep types. Interpolating is used for broad frequency sweeps, and fields are always available, or fields are available only at solution frequency, I'm sorry. Whereas in discrete sweep type, the fields are always available at all frequencies if you choose to save them. And the fast sweep, again, fields are available if you choose to save them at all frequencies. If you want to cover a broad range, interpolating is your best option. If you want to have a somewhat limited range, and if you're interested in fields, fast is your best option. And if you're only interested in a few frequencies, discrete is your best option. But keep in mind, discrete solves at all frequencies, so it will be your slowest option for simulation time. The convergence criteria that we're going to talk about next is over here under setup. We are interested in total number of passes, which is set to 20 here. And then we're also interested in minimum number of passes. That I usually set to 2. And then minimum number of converged passes, I also set it to 2 usually to avoid any doubts if the error function is moving up and down in a zigzag motion. I want to make sure that it's a stable solution. So I set it to 2. That means after convergence, it does 1 extra pass. And then delta S would be chosen here. 0.02 is probably okay for antenna simulations, but if you're simulating waveguides or enclosed structures and you want more accuracy, you would want to set that to lower values like 0.05. And lastly, if you have the HPC license available, I would make sure that the number of cores are set to the maximum that the PC can handle. This particular PC has 6 cores. That's why I have it set to 6 over here. Because you want to take maximum advantage of your hardware. And finally, after all of that is done and the simulation is run, after the analysis, we can take a look at a variety of parameters in the post processor. Obviously, we can take a look at S11 data. Here I had run a sweep of the ground plane size, I believe. No, actually it's the offset, the feed offset. So I'm displaying S11 results for all the offsets, different offsets. That means where the feed is with respect to the center. Can also have radiation efficiencies plotted for all the parameters, for the offset parameter in this case. I can also have surface currents displayed on structures, and it's also possible to animate these currents for different phases. For the edge-fed case, for example, we can look at the antenna gain, 3D gain plot, and it's also possible to overlay this plot above your structure like that, and you can change the scale of that, no problem. Over here, we can make it larger. And there are other antenna parameters available under this report here, such as peak gain, different definitions of gain and directivities, radiation efficiency as we've seen before. And you can plot any of these for the different parameters sweeps that you've chosen to run. So finally, I would like to talk about common mistakes that are made during the simulation setups. One common mistake is that no airbox is defined. I've mentioned this before. If you don't define an airbox, HFSS chooses to terminate the domain with PEC, which would short circuit your antenna or your circuit. Similarly, you may have the airbox, but you don't have a radiation boundary defined. So then your airbox will become metal, and your simulation domain will be inside that metal. Or you may have forgotten to assign materials, or have given the wrong material in the assignments, in which case the non-assigned geometries will be treated as vacuum. And one thing I want to mention is you may also have gaps in between metals that are intended to touch, such as this one over here. If there were two pieces here, you know, the feed is coming to the patch, and if there was a gap here, and you know, that would cause no connection, and it would cause problems with the simulation. Even though it's a tiny gap, it's still not electrically connected, so it would cause different issues, different results in the simulation. So I would make use of um, these snapping features over here in the tool when drawing objects. See if I can illustrate something. Example, if I want to draw a rectangle, see, I can't snap to this corner. If I can snap, if I can choose these snaps features, I will be able to snap. Let's see. There, I snapped to that corner right there. So when drawing, I would always use these snap features as much as possible, and avoid entering the dimensions numerically while you're drawing. Another common mistake could be errors in port definitions, such as no connection or shorting. For example, in the case of the HFIT model, if my port is not, if this rectangle is not touching the ground plane, that would cause a problem with the results. Or if the port is not covering or touching the inner conductor, that would cause problems. In the case of the coax as well, same. If my wave port is not touching the outer conductor over here, it would result in a different simulation than I intended. So my advice would be to always investigate and understand the root cause of every warning message also in this message manager window. When you're running the simulation, always monitor this window and question everything there that's coming up as a warning or an error. So with this, I'll open the floor for questions. See, I don't see any questions being typed, but are there any verbal questions?
Yeah, Mete, question that came up. What about, what are the other solvers available in HFSS? You mentioned this was one of them. What other solvers are available?
Yeah, so there are also, this is an FEM solver, but there are also uh, uh, solvers. There's a time domain solver. There's also SPR Plus, which is used for electrically large objects. For example, you solve your antenna using HFSS, and you want to place it in a room or an airplane. You could use a solver called SPR Plus to to use your solve the antenna, electrically larger problem. Are there any other questions?
Yeah, I had one other one. When you're talking about HPC, how does that work on different computers? Is there a big advantage to speed in every simulation, or does it depend more on the exact simulation? Kind of wanting to know when is HPC advantageous?
Okay, so there's when the problems have problems require big memory, large memory, then there's definitely advantage in sharing the tasks between different computers. But if the problem, so if it really depends on the problem, if there's parallel processing available, such as multiple ports, you definitely take advantage of having different computers run different excitations in parallel. So there's definitely a limit there. You cannot have infinite number of PCs to speed up your simulation, but you don't get like twice the speed, but you'll definitely have higher speeds in some problems, a lot higher speeds in some problems by using multiple computers. And this is where you set them up here. You can just add different PCs here if you have the HPC license. It looks like there's another question here.
Yeah, there's a question in the question panel.
Yeah, the question is how to see the impact of temperature on antenna performance. I'm not the expert in thermal analysis, so we can get back to you on that. We can either contact you via email or give you a call with an answer.
Let me.
Yeah, Mette, do you have the contact info for the gentleman with the temperature question?
Oh, yeah.
Yeah, if anyone has a question, you can unmute yourself and ask the question.
Hey, Mette, the question is, the electric property, the electric material, can that be temperature dependent?
Oh, yeah. All of those materials can have, for example, if we go back, I don't typically use these, but there's the substrate FR4, for example. You can have different properties defined here for each material.
And that property is temperature dependent.
No, this is not temperature dependent. What I have here is not temperature dependent. But you can have a thermal modifier, I guess.
Okay. So the thermal modifier could be attached to an ANSYS thermal solution, maybe. Is that what you're saying?
Yes, that's what I'm saying. Yep.
Okay. Yeah, we'll get the contact info here for Iftikhar. Yeah.
We'll definitely get back.
Okay, yeah, and if anyone, you can unmute yourself if anyone wants to ask another question. Let me- So if there's no more questions, again, thank you everyone for attending. Have a good Easter weekend. This session was recorded, so you can access it on the Mallet website at www.mallet.com in our webinar section. That'll be available probably later today. Our next webinar is in 3 weeks. We thank you for coming and take care.
Thank you very much. Happy Easter.